right, guys, we are going to add to our notebook again. So last time we talked about graphing systems of inequalities, and now we're going to talk more about like what it means to be a system and how we solve a system graphically. So graphical solutions of systems. And we will do that on page 69 and 70. Okay, so if we turn the page, we got 69 here, 70 here. Let's actually start on 70. So we want to ask the question or like answer the question, what is a system? And essentially what a system is more than one thing. So like we were looking at equations last chapter, y equals 2x plus 7. There are two variables there, and I can't solve for both of them unless I know one first. So if I want to solve for two letters, I need to have two equations to do it. And if I wanted to solve for three letters, I would need three equations to do it. And if I wanted to solve for four different letters, I would need four equations to do it. And that would get real crazy and not something that we're going to do in this class, but it's something that I did do in college where I had to solve for four different variables by using four different equations. So what we're going to try, though, is where we solve for two different variables, like solving for x and solving for y. But to do it, I need to have two different equations. That's essentially what a system is. A system is multiple equations to help solve for multiple variables. And again, guys, it always matches up. If I want to solve for 3 variables, I need 3 equations. If I wanted to solve for 10 variables, I would need 10 equations to do it. Now we're just going to do 2 and 2. So when we think about this graphically, what we will always have are 2 lines, because if I'm solving for x and y, that means I have an x and a y in my equation, and that's what we were talking about all last chapter, like y equals mx plus b stuff. So when we are thinking about 2 lines on a graph, there are kind of 3 things that could happen. You might have that your line, like your 2 lines, end up crossing each other, and they might cross each other perpendicularly, or they might not, but they cross each other, and that one spot that they cross at is their one solution. Now, if you remember, we talked last chapter also about lines not crossing. And so lines that do not cross are parallel. And since they don't cross, they don't have a solution, because you're always looking for that point that they touch at, and that's my solution. So since they don't touch, they have no solution. Now, the last thing that can happen is actually kind of weird. And we did talk about this when we were talking about parallel and perpendicular lines very briefly. But what might happen is that I have a line, and then when I go to graph the other line, it ends up right on top of the first one. And they're essentially the same line, but it's like a line on top of a line. And since it's on top of it, it's touching all the time in all the places. So that means you have all of the numbers on here that are solutions. And since the line goes on forever, you have infinite solutions. Or you could say like all real numbers as the solutions, which hopefully we know that that sideways 8 is a symbol for infinity. So infinite solutions. So kind of the mathy terms for this, and guys, I'm not super like picky when it comes to knowing mathy terms, but just in case, the mathy terms for having a solution is to be consistent. So if you are a consistent system, then that means you have a solution. So there is a solution. There is a solution. And the reason I have it twice is because for an example like this, there is a solution, but there's only one. So if you are consistent, independent, then that means there is a solution and there is only one of them. So one solution. Now, the other type of solution that you can have is consistent dependent, which is when I have infinite solutions because they are touching all the time. Now, the only other option is that you don't have any solution at all. And so when I have no solution and those lines are parallel, you are inconsistent. So not consistent is inconsistent, and that means there is no solution. And you wouldn't call it dependent or independent because it doesn't have a solution or infinite solutions. It has none. Okay. So if we take a look inside here, we just got a whole bunch of graphies to do. Luckily, a lot of them are in y equals mx plus b. So we got y equals mx plus b here. My y-intercept is at -1. My slope is 2, so up 2 over 1. And then this line has no slope. It's just going to go through -3. Boop. And because they touch once, it has a solution, and there is one. So they are consistent, independent. And the solution is right here where they cross, which is at like an x comma y, and it's like -1 comma -3. So that is exactly where your solution is. Another example of that could be over here. So if we graph this line, this has a y-intercept of 1 and a slope of 1. So I go up 1 over 1. And I always like to do lots of dots on these ones. I didn't mention that on the last one, but I like to do lots of dots because then if the other line lands exactly on a dot, then I know exactly where my answer is. So like this one here has a y-intercept of -3 and a slope of -1. So down 1 over 1 or up 1, back 1. See, and again, then I can see right where the dots are the same. So because I have one solution, it is consistent. Oh my gosh, I can't spell. Independent. And your solution is right where they touch each other, which at x comma y is -2 comma -1. Okay. So some examples of consistent dependent. If we take a look at this first one here, that is in y equals mx plus b. So I can plot the y-intercept at -1 and do my slope of up 2 over 1 or down 2, back 1. And then the bottom line is not in y equals mx plus b. That's in standard form. So when you're in standard form, the way that I like to graph real quick is I ignore y and solve for x. So I would have to divide by 2 on both sides. So x would be half, which is right here. And then to solve for y, I would have to ignore x and divide by -1. So -1 is right here. And I'm pretty sure that line is going to be right on top of it. Now I can also know for sure because if I rewrite this as y equals mx plus b, I would subtract the 2x both sides, and I'd have -y equals -2x plus 1. And then I need to change all the signs so that y will be positive. And when you do that, you end up with the exact same equation that we had to start with. So because of that, I do have a solution because they're touching all the time. So this is consistent dependent. So consistent dependent. And the solution is infinite because like all of them touches in all the spots. Okay, so another example of this, we got this one right here. That's in y equals mx plus b. My y-intercept is at 5. My slope is -2, so I'll go down 2 over 1. Get a whole bunch of dots. Now the other line is in that standard form again, so I could solve for x by ignoring y and then dividing by 2. So 5 over 2 is 2.5. So I go to the x at 1, 2.5. And then if I solve for y, I ignore x, and y is already solved for, and it's 5. So again, I think these lines are right on top of each other. And if you want to solve for y in that bottom one, like we would just subtract the 2x. And I think we would see that we have the same exact equation up here, -2x plus 5. So when they touch all the time, that is consistent. I keep forgetting that second S. Consistent dependent. And they have infinite solutions because they're touching all the time. Last but not least, if we go over here, we have this first one is in y equals mx plus b and starts at -1 and has a slope of up 2 over 1. Down to back 1. The second line has a y-intercept of +1 and a slope of up 2 over 1 again. So as far as I'll go, they will never touch because these lines are parallel. And I can kind of tell that beforehand because they had the same slopes, but different y-intercepts. So because they're parallel lines, they will never touch, which means that they are inconsistent and have no solution. Okay, so last one to try over here. Maybe I'll get both of these in y equals mx plus b. So like I'll subtract the 3x here. And we'll have y equals -3x plus 4. And then on this bottom one, and I know I can go graph that, but I want you guys to see something. If I subtract the 3x down here, we'll have y equals -3x minus 2. I know right now, without even graphing, that it will have no solution and they will be parallel lines because these have the same slope and different y-intercepts. And that's what we said had to be true about parallel lines. So I really don't even need to graph it to know that it is inconsistent. Oh my word, consistent and has no solution. Now, what I would suggest doing is trying out some of these ones over here on page 69 because there's just a whole bunch of examples. And then I will post a separate video where I go through and do them all, but I'm going to do them pretty quickly so that you guys can just kind of check and see how you do. I just don't want this video to be too long. All right, good luck.